So when we're constructing these circuits, there's at least a minimum of two conductors, one used as the supply and one used as the return per phase, right, or per load in the three-phase system. So you may have already kind of pieced together that there really are then two different ways that we can choose to connect the loads when we're using these polyphase systems. The loads can be connected between one phase and the neutral connection of the polyphase connector, or the load can be connected between one phase and the second phase. So what we're going to do now is we're going to look at the two possible load and voltage source configurations or power configurations for Delta and Wye, which are called Delta and Wye connections. So we're going to look at these very, very common, what are called the three-phase configurations. So in both cases, in either the Delta configuration or the Wye configuration, a three-phase source will supply the three separate loads. The first arrangement, where the three-phase loads are connected between one phase each and a ground, is called a Wye connection. So we see that there would be a supply here, and the load is connected between a neutral point and a line. So in that arrangement, the loads are connected between one phase and a ground, and this is called a Wye. And it's easy to remember because its schematic shape forms the letter Y. It looks like a Y. Right? The arrangement in which the three loads are connected between one pair of the phase voltages is called the Delta connection. So you see this load, there is no neutral, and we've connected the load between two voltages, right? So this is called the Delta because it looks like the Greek letter delta. Right? You're used to seeing in derivatives. The choice of either Y or delta will have significant ramifications on the resultant load voltages and currents of the polyphase system when we apply KVL and KCL. And additionally, I want to point out that the same configurations, Y and delta, they're not just applicable to loads. The sources also have to be connected in three-phase, and so sources can be used to supply, the three-phase sources used to supply these loads can also either be connected in Y or delta. The following discussion that we're going to have and the circuit analysis techniques that we're going to present will apply equally well to both sources and to loads. Right? So, I would just want to develop some terminology on this slide here. Here I've shown some Y connected sources, and I've shown a Y connected load as well. In a Y or a delta connected system, the conductors leading away from the source, that's this wire here, this wire here, this wire here, 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 and here, are called lines, while the voltage sources themselves, here, here, and the loads themselves, this here, didn't mean to leave out this guy, sorry about that. They're called phases. When we measure the voltage and currents in these three-phase systems, we need to specify where we're measuring or where we're taking our measurement in reference to. A line voltage refers to the amount of voltage measured between any two line conductors. So a line voltage would be a voltage measured from this line to this line. If I took one probe of my DMM and I put it on that line, and I took the second probe of the DMM and I put it on that line, that would be a line-to-line voltage. I could also measure a line-to-line voltage from the top line to the bottom line, or from the middle line to the bottom line. Those are called, again, line-to-line voltage. Often this is just shortened to the line voltage, and line voltage refers to the amount of voltage measured between any two line conductors. The term phase voltage is the measurement across any one component, either a source or a load. So the phase voltage would be here, here, and here. That would be the phase of the load, phase voltage of the load, and the phase voltage of the source would be measured here, here, and here. There would also be line voltages at the source, line voltage, line voltage, line voltage. So in each of these configurations, there's 3 line voltages, there are 3 phase voltages. The terms line current and phase current follow the same convention, where a line current is the current through any one line, right? Right there, those would be both line currents. And the phase current is the current through any one component. So if the current's flowing through a component, that's the phase current. Y-connected circuits will always have line voltages that are greater than the phase voltage, and will have line currents that are the same as the phase currents. Assuming that the Y-connected load is balanced, the line voltage, right here, is calculated as the phase voltage times the square root of 3, and the line voltage will lead its associated line to neutral voltage by 30 degrees. For these Y circuits, we therefore say that the line voltage is equal to the phase voltage times radical 3 at an angle 30. So if I know the phase voltage, for instance 120 volts, and I want to know the line-to-line voltage associated with that in reference to 120 volts angle 0, it's going to be 120 angle 0 times radical 3 angle 30. As we can see, the phase current and the line current, well, they're the same thing. So in a Y connection, the line current IL is equal to the phase current. I'm just saying the current here is the same as this. Why am I making the distinction? It won't be the case in the delta circuit. Here the line current is, the phase current is the same as the line current. Right. The connection shown for the Y circuit is that on this last slide with the neutral is often called the 3-phase 4-wire, this 4th wire being the neutral. Y circuits can also be constructed without the neutral, and this arrangement is called 3-phase 3-wire. And the terms line and phase and everything still apply. It's just we've eliminated the neutral because in this circuit because the neutral current is 0 in a balanced 3-phase system, and therefore, strictly speaking, that neutral wire is unnecessary if the load is balanced. The second load source configuration again is called the delta configuration, and the phases do not share a common connection, right? There's no neutral point in here, and therefore there is no neutral wire at all in the delta circuit, right? It just doesn't exist in this thing. Because in the delta configuration each pair of line conductors is connected directly across a single winding, the line voltage and the phase voltage are the same thing, right? If I were to measure the voltage across an element, which is the phase voltage, and the voltage across or from one line to another line, that's the same measurement. So in a delta circuit, the phase is equal to the line voltage, right? Conversely though, because each line conductor attaches at a node between 2 windings, the line current has to be calculated using the vector sum of the 2 joining phase currents. What we're saying there is if I've got current flow in this element, that would be the phase current. This is the line current here. There's also a phase current right here, right? So this current has to be the vector sum of those two, right? We now know that they have magnitudes and angles, and so using KCL at that node, we have to say I line is equal to I phase 1 plus I phase 2, knowing that those are complex numbers. The result of this math also will indicate that the line current lags the phase current. This result will also show us, if we were to perform the math, that the line current here is going to lag phase currents by 30 degrees. And for a delta circuit current calculation, we therefore get IL, the line current, is equal to radical 3 angle negative 30 times the phase current. So the voltage and current relationships are flipped in the delta circuit. Remember, in the Y circuit, V phase is equal to, V line is equal to V phase times radical 3 angle 30, and the line and the phase current are the same. Whereas in the delta connection, the phase voltage and the phase, the line voltage are the same. Phase voltage and line voltage are the same, but the currents are different, and they're related by that radical 3 at an angle of negative 30 degrees. Because three-phase sources and loads can each be configured as Y or delta, there are therefore 4 basic three-phase circuit configurations that we can come up depending with whether the source or the load is connected. Although we haven't explored this in much detail yet, voltage sources, by this I mean generators, and loads are typically connected to the power system through step-up and step-down transformers. Internally, these transformers have what's called a primary and a secondary winding, and these windings for three-phase arrangements can be configured in either Y or delta as well. The use of the Y and the delta configuration is not only useful in obtaining different voltages, as we've seen, right? We get that radical 3 step up between the phase and the line voltage if we want it, or changing the currents. But it's not only useful in obtaining that different voltage level, but it also has ramifications regarding the reliability of a circuit in case of a short circuit. We'll first note that there is no neutral connection in a delta circuit, and as a whole it is ungrounded or floating, right? On this circuit there's no neutral. As a whole there is no reference node, there's no ground node. The entire delta circuit can therefore float at any arbitrary value of potential. And therefore, if any part of the circuit accidentally gets grounded, which would normally cause an outage, the delta circuit can continue to operate on an emergency basis. You therefore often see delta circuit configurations used where reliability is the most important. The Y configuration, on contrast, is normally grounded at this center point. It's pretty common to go ahead and ground that. Here, a single ground anywhere else in the system will immediately cause a fault.